In this video, we're going to learn how to create a regression tree. In the last video, we created a tree for a binary response. In this video, we're going to create a tree for a continuous response. And again, that's called a regression tree versus a classification tree, which is what we created last time. We're going to use the same function we used for our binary predictions in a classification tree. This time, same code, same storage. We're still going to call the model fit. We're going to use rpart, the decision tree function, which again stands for recursive partitioning, just an interesting computer science terminology. We're going to use the same model formula that we used before, but this time we're going to make sure that our response, that thing we're trying to predict, is continuous. This is the donation amount. It's the dollar amount. It could be $40. It could be $200,000. We're going to specify that data set here. Data equals ttrain instead of using ttrain dollar in front of every variable. And finally, when we type method equals ANOVA, it's a regression tree. Before we used method equals class for a classification tree. ANOVA means analysis of variance. It's a very common terminology. Why we're using it here, I'm not exactly sure, but I can tell you that when functions are open source, the way R is, different people assign different meanings according to what they think is the most obvious, meaningful thing, but that's not going to be obvious and meaningful to everyone. So for a classification tree, we use method equals class. For a regression tree with a continuous outcome like this one, we use method equals ANOVA. So the only differences are the response variable and the method equals statement. We could print out the tree the same way we did before using the plot and the text functions. Plot is going to show the actual tree and text is going to fill in the decisions and the predictions. So you can see again, household income is the first decision, but here the first split value is, it looks like $111,500. Again, I don't know how to get rid of the scientific notation in the tree labels. It's possible that there is a command to do that. So we split on household income a few times, but one of the things I want you to notice is that the label here is already cut off and we have a relatively small tree. It's not cut off because I cut it off, it's cut off because it would only print this size tree. So we already are running into limitations when we try to view the actual tree. And again, there's not that much information we can take away. What you will notice is that just by design, a lot of different observations are going to come down into this bucket and have a prediction of $507.50. So even though it's predicting continuous values, it's going to make the same prediction for lots of different observations. Making predictions follows the same structure that we did for the classification tree, the prediction of a yes or no outcome. The in-sample predictions use the predict function. We use the model and the training data. But this time, the predictions are going to be actual numbers because we have a continuous response. So method equals ANOVA is actually going to force the predictions to have a number value instead of giving probabilities. So you can see for the first observation in that data set, we're still using the same observations for the training data. The first one is prediction $507.50. And the second one has the same prediction and the third one has the same. So for the first three, we're predicting the same outcome. It's probably not going to have the same actual outcome, but the predictions are the same. The out-of-sample predictions can be made in a similar way with the test data instead of the training data. Now remember, when we predict continuous outcomes, we actually have continuous outcomes that we can compare. So if we say we make a prediction of $507.50, but someone donates $350, well then we were off by $157.50. So we can measure our errors in a continuous way, just like linear regression, where we would construct a histogram and take the average error. In our linear regression for predicting donations, we would find the following coefficients. All of them are significant, and we can write the donation amount as a function of the intercept and various coefficients times their predictor variables. One thing I noticed right away is that the intercept is negative. It's interesting that when your age is 0 and your income is 0 and you're not employed and you don't have any dependents, that you're expected to donate some negative amount of money. And that's really impractical, but so is having someone in the data set that's got an age of 0. So it's not really uncomfortable, it's just something to notice. I also see directly that age would decrease the expected donation amount, income increases the expected donation amount, etc. So let's compare the models. For a linear regression, the average absolute error is $164. So just like on your last exam, when you were studying predicted errors in donation amounts, we said $150, $165. That's a big error if my average donation is small. If my average donation is really big, then being off by $165 really isn't that big of a deal. Now that's the in-sample, that's in the training data. Let's compare it to the test data. In the test data, the standard deviation goes up a little bit, but that's expected, and the average actually reduces. A reduction out of sample doesn't necessarily mean the model is better on new information. It's like if Tiger Woods plays a brand new golf course for the first time, we're not going to expect him to be better on that new course than he is on a course that he plays regularly. It could just be a fluke. But if he played his home course, we would expect him to be better there than other places. It's the same thing with a model. The first time a model sees data is a really good evaluation of how well the model does. On data that it already knows, the data that it's been trained on, like the in-sample training data, we expect it to know that as well as it can possibly know anything. So the fact that our out-of-sample error on average is smaller than in-sample, it's like, okay, it's doing as well as it would on data that it's seen before. Just like Tiger playing on a new course, if he does the same, beating par by some number of strokes, and he's performing the same on a new course as he does on an old course, it's like, okay, wow, he's really showing that he's a great golfer. He can handle anything. Now let's compare the linear regression to our tree. For the in-sample error, the average mistake made by the tree is $200, over $200. And out of sample, it's about $190. So what I can say that is different from the binary classification tree here is that it's clear that the tree is not doing as good a job as the linear regression. So for this particular situation, I'd say since the linear regression on average does a much better job, let's just use the linear regression. But it's good to have something else to compare to, and we're going to talk about why in the next video.